Hello. Today we're going to talk about relativity and what the Lorentz-Fitzgerald contraction means. Here's a disclaimer. The material is based on sound scientific principles. The opinions expressed here are mine, based on the observations we are going to make. This presentation has not been peer-reviewed or accepted by any journal. The information in this presentation is general in nature and not intended as professional guidance, nor will it assist you in passing any exams. You are encouraged to confirm any information obtained from this presentation with other sources, and this material is copyrighted. This presentation will address the concepts of momentum and energy and how the Lorentz factor is applied to them. We will then define relativity and introduce an old video game called Paperboy. We will use this game to derive the Lorentz factor and apply some meaning to its use. From this, we will explore other ways to complete the game by modifying the Lorentz factor and show some interesting possibilities into the speed of light and information. We will next show a derivation for E equals mc squared using the Lorentz factor. Finally, we will explore an alternate formulation to the Lorentz factor and see where it leads. The information from this slide comes from Wikipedia. We define the relativistic momentum P as mass times velocity. The mass is attributed to the Lorentz factor times the mass measured when the object is at rest. We define the relativistic energy as the Lorentz factor minus 1 times the rest mass multiplied by the square of the speed of light. The literature is very confusing regarding the Lorentz factor. Writers will attribute it to any of the base units, mass, length, or time, depending on their own bias. It can only be applied to one of these units, but which one? Some science texts write that mass increases with motion. An object with mass can never reach the speed of light because its mass approaches infinity, meaning that it would take an infinite amount of energy to push it faster. Because E equals mc squared, the implication is that kinetic energy is being converted into mass. Mass is a difficult quantity to measure directly and is usually inferred by its momentum or energy due to a collision or other event. Yes, particles seem to appear out of nowhere in a particle accelerator, but this seems too magical. Some science texts write that time slows with motion. The twins paradox is the classic thought experiment where time is expected to slow down for a moving object. This interpretation implies that clocks on the moving platform move more slowly than when they are at rest. Most of these inferences come from relativistic particles that seem to last longer than they should because they are limited by the speed of light. In our previous presentation, Physics 02, we showed that observers perceived other clocks to vary with velocity due to the Doppler effect. We will discuss how it may be possible for objects to move faster than the speed of light later in this presentation. If this were true, time might not be slowing down. We might just be inferring this based on an incorrect estimate of velocity. Some science texts write that length decreases with motion. This interpretation indicates that lengths on a moving platform are shorter than they are at rest. In our previous presentation, Physics 03, we noted that length contraction was inferred by the Michelson-Morley experiment, and that the speed of light was universal in all inertial frames. We will now demonstrate that the Lorentz factor translates lengths between different inertial reference frames. We will need to define inertial frames to discuss the Lorentz contraction, but first let's define relativity. Relativity is defined in Wikipedia as the laws of physics are the same for all observers in any inertial frame of reference relative to one another. This means that no observer that is stationary or experiencing uniform linear motion can see a difference in the equations of physics. These equations are used with differences attributed to their different velocities. I interpret this as similar, if not equivalent, to the principle of reciprocity. An example of this is that an antenna pattern is the same whether it is transmitting or receiving. Most of this material comes from Wikipedia's articles on relativity and reciprocity. It is not unusual for an observer to use a measurement system that is stationary. In this graphic, we note two observers marked by blue and red dots. One observer is moving with respect to the other. On the left, blue sees himself at rest with red moving, and on the right, red sees himself at rest with blue moving. Either frame is correct and equivalent. As in previous presentations, we note that the same event is perceived differently depending on the observer. An independent observer might see both moving with respect to this top-down view. It is impossible to tell which observer is actually moving, nor is it necessary. Relativity requires only that we define what the movement is with respect to, and we have plenty of choices. We will now introduce our case study. There are several equivalent scenarios that we can examine here. The first is a paper boy throws a paper at a stationary porch while riding his bike. The second might be a bratty kid sitting on the curb throwing rocks at passing cars. These problems have the same solution since a choice of reference frame is not necessary. However, we will focus on the former problem so as not to condone bad behavior. The object of the game of Paperboy is to toss paper onto a porch while on a moving bicycle. Let's say that the boy on the bicycle moves horizontally and a paper is tossed vertically on the screen. In the graphic on the left, the reference frame is with respect to the Paperboy. The Paperboy, our blue dot, is stationary and sees the paper, the green dot, moving perpendicular and away from him. A man sitting on his porch, our red dot, runs into the paper. This is consistent with what we learned in Physics 03. In the graphic on the right, the reference frame is with respect to the man on the porch. He sees the paper coming at him from an angle while the paper boy moves past. Each observer measures a different path and length. The geometry forms a right triangle. We assume that our man on the porch can measure the lengths of B and C. We can then solve for A using Pythagoras' theorem. These lengths can be related to the relative velocities over time. Note that time drops out of the equation. We can then solve for A from the other parameters. The ratio of the two lengths is C over A. This is how we translate length between different inertial reference frames. This graphic shows a plot of the Lorentz factor labeled gamma. It has a real solution for values of V over C between 0 and 1. This means that there is a solution for the equation for V, the paperboy's velocity, between 0 and C. Each observer records the same event, but derives different measurements. There is no solution for V greater than or equal to C. Because of the way the geometry is defined, we deduce that the paperboy cannot exceed the velocity of the paper. But in practice, this means that the paper cannot land on the porch unless the paperboy moves slower than the newspaper. To make our analogy clear, the math states that we cannot observe anything that moves faster than the speed of our information. This problem is defined such that the paper is thrown perpendicular to the motion of the bicycle. However, we could throw the paper behind us to compensate for any excess speed. There are still a range of angles for which we can throw the paper and still land it on the porch. Here is an example where the paper is thrown left and back and lands on the porch. Note that the green trace on the right looks a lot like it did in the previous example. We'll make use of the law of cosines. Pythagoras' theorem is included in this math if we let theta equals 90 degrees. We note that while the paperboy is now allowed to move faster than c, the man on the porch might only see him moving with speed c, and yet the paperboy has traveled much farther in the allotted time. Is this how time dilation works? We now append these results to the previous graph of the Lorentz factor. Based on this, it is theoretically possible to travel infinitely faster than c, even though our man on the porch might not know that we did. These graphs show the Lorentz factor by color bar for values of v over c and throwing angle. Because we solved the quadratic equation, there are two allowable values for throwing angle when the speed is greater than c. Areas in white are conditions where the paper cannot hit the porch. No solution exists. This is a variation of the previous graph. In it, we show the throwing angle by color bar for values of v over c and the Lorentz factor. Again, areas in white are conditions where the paper cannot hit the porch. We have made the claim that the Lorentz factor allows us to translate lengths between various inertial reference frames. We will now use this to show how to derive E equals mc squared. It is well known that one can integrate the momentum over velocity to get energy. We will compute how much energy is required to change the momentum of a particle having mass m from 0 to c. Recall that relativistic momentum is equal to mass times velocity times the Lorentz factor. In classical physics, this would integrate to 1/2 mc squared. Because of the Lorentz factor, when we integrate this from 0 to c, we get E equals mc squared. It does not take an infinite amount of energy to get to the speed of light. However, the amount required is still rather prohibitive. That is all I really have to say on this topic. What I have said so far does not fit the general consensus by physicists. One thing that always bothered me about the way the Lorentz factor was set up was the problem when v equals c. I suppose the problem was designed for the man on the porch. After all, the physicist is always the man on the porch, waiting for his newspaper to be delivered. So it makes sense that lengths c and b would be the measurable quantities, and a would be the term that was solved for. The other reason why this problem exists is that it was legislated a long time ago that the speed of light was a constant that could not be exceeded. Using our top-down view approach, as we have in previous presentations, I might set the problem up in a different way and avoid the divide by zero. Perhaps this additional material might serve as a discussion point for the interested viewer. In this alternate math, we know Pythagoras' theorem applies, and it follows that the square of the hypotenuse, labeled d here, is equal to c squared plus v squared. This avoids the divide by zero problem, but presupposes that all quantities are measurable. In this case, a is deduced to be the speed of light, and c is some value greater. This would be consistent with conclusions reached in previous presentations. The question remaining then is, why don't we ever measure anything greater than the speed of light? And that will be a topic of a future presentation. This slide then augments the previous slide by introducing the law of cosines and non-perpendicular throwing angles. The Lorentz factor has been modified as shown. The consequence of this alternate solution is that the mass-energy equation is off by a small amount. Now we get E equals 0.61 mc squared. In this presentation, we showed how the Lorentz factor is used to translate lengths between different inertial reference frames. We then derived Einstein's equation for mass and energy. We also showed that it may be possible to move faster than the speed of light, but other observers might not recognize it. Finally, we explored an alternate solution for the Lorentz factor. If you found this presentation interesting and/or informative, please like and subscribe. Thank you.